The engineer put the board down because it was too hot. What is it? The board, obviously, not the engineer. You resolved that instantly, using nothing but the other words in the sentence. Every word you read adjusted what the others meant. A model has to do the same thing, and its input, as we saw last time, is just a stack of vectors. No grammar, no rules, no notion that it is even a pronoun. So, how do you build a mechanism that lets each position look at the others and pull in what it needs? We're going to derive it, not describe it, derive it. Here's the input, exactly where the last video left off. 1 row per token, each row a learned vector, no structure beyond that. We want an operation that produces, for each position, a new vector, one that has absorbed relevant information from the other positions. 3 constraints, and they're worth stating because they eliminate almost everything. 1. It must be differentiable. The whole model trains by gradient descent. Anything with a hard if statement or a discrete lookup is out. 2. It must handle any sequence length, without new parameters when the sentence gets longer. 3. It must be parallel, every position computed at once. Sequential models existed and were abandoned partly for this reason. So we need something smooth, length-agnostic, and parallel. That's a narrow target, and it turns out there's a fairly natural thing that hits it. Before we build anything, 30 seconds on notation, because the formula at the end is unreadable without it, and readable with it. Bold lowercase means a vector. Not one number, a whole list of them, 4,096 of them in our case, describing one token. Plain italic means a single number, a score, a weight, a count. Bold capital means a matrix, a grid of numbers that turns one vector into another. That's the entire convention, and it carries the whole video. When you see bold, think list. When you see plain, think one number. 2 more names. Our sentence has some number of positions, we'll call that count n. 11 here, and each token's vector has some length, which everyone calls d, the model dimension. Throughout, we'll follow one position, the word it. That's the position doing the looking, the one that needs to find its referent. Everything we build for that position first, then note that it happens for all of them at once. The crudest thing that satisfies all 3 constraints. For each position, take the average of every vector in the sequence. Differentiable, length-agnostic, parallel, it genuinely satisfies the brief. It's also useless. Averaging says every word is equally relevant to every other word. So the new vector for it is 1/11th engineer, 1/11th board, 1/11th down, 1/11th hot, and so on. But it needs the board far more than it needs down. A uniform average destroys exactly the information we wanted. The defect, the weights are fixed. Every weight is 1 over and no matter what the words are. We need weights that depend on the content. So instead, let each position produce its own weight for every other position, and take a weighted average. That's the shape of the answer, and it's worth reading carefully because every remaining beat is about one symbol in it. The new vector for our asking position is a sum over every candidate position of a weight times that candidate's vector. Big weight, that candidate contributes a lot. Weight near 0, it may as well not be there. Everything from here is working out where those weights come from. So we need a number for every pair. How relevant is this candidate to the asking position? We have vectors, and there's an obvious way to turn 2 vectors into one number that's differentiable and cheap, the dot product. Multiply the 2 lists element by element, add up the results, and you get a single number. What that number means geometrically is the useful part. 2 vectors pointing in similar directions give a large dot product. Vectors pointing in unrelated directions give something near 0. And vectors pointing in opposite directions give a negative number. So it's a similarity measure that we get essentially for free. So, score every pair by dot producting their vectors, and use those scores as the weights. For our sentence, that's 11 positions each scoring against 11 candidates, an 11 by 11 grid of numbers. The row for it is the one we care about. 11 scores saying how much it cares about each word, and we'd hope the one under board comes out largest. Better, the weights now depend on content, which is exactly what the last beat asked for. But there's a defect, and it's the subtle one. A vector is being used for two different jobs at once. Think about what happens when it scores board. The vector for it is playing the role of the asker. It encodes what it is hunting for, which is a concrete noun somewhere behind it. But that exact same vector, one row up in the grid, is being scored against. It's playing the role of the advertiser, encoding what it offers to anything looking at it. Those are different things, and for a pronoun, they're almost opposites. It is a poor advertiser of meaning. It carries almost no content of its own. But it's an eager consumer of meaning. It desperately needs something else's. One vector has to encode both at once. Whatever it does to get better at asking makes it worse at advertising. The model can't get good at either. So instead, learn two separate projections. From each token's vector, compute two new vectors. The first is the query, what this position is looking for. The second is the key, what this position offers to anyone looking. Both of those are matrices the model learns during training. Nobody specifies what a query should contain. Gradient descent works out that pronouns should query for nearby concrete nouns because doing so lowers the loss. Same input vector, two different learned views of it. And now we score query against key rather than vector against vector, an asker's question against an advertiser's pitch. That's Q and K. They exist because one vector can't play both roles. We have weights, now, weighted average of what? The obvious answer is the original vectors, but the same argument applies one more time. What a token offers as a matching target and what it contributes once matched need not be the same. Board might be easy to match on because it's a concrete noun, that's what makes it a good key. But what's actually useful to hand over to it is something else entirely, that it's an object, that it's physical, that it can be hot. Matching and contributing are separate jobs, so they get separate vectors. So instead, a third learned projection. The value, what this position actually contributes when something attends to it. Three projections of the same input vector, three jobs. Query, what I'm looking for key, what I advertise value, what I hand over. That's Q, KV, not arbitrary letters, three distinct roles that were tangled together in one vector and had to be pulled apart. One problem left with the weights, and fixing it needs a tool we haven't met, so let's meet it properly rather than waving at it. The scores aren't weights. They're arbitrary real numbers. Some are negative. They don't sum to anything in particular. A weighted average needs weights that are positive and that sum to one, otherwise you're not averaging, you're just scaling the answer by an arbitrary amount. So we need something that takes any list of numbers and returns a list that's positive and sums to one. That thing is the Softmax, and it works in two steps. Step 1, exponentiate every score. Raise e to the power of each one. The exponential is positive for every input, negative scores come out small but positive, so the sign problem is solved. It also stretches the gaps. Because the exponential grows fast, a score that was modestly ahead comes out dramatically ahead. Step 2, divide each result by the total of all of them. Now they sum to 1 by construction. That's the whole function. Exponentiate, then normalize. Two properties matter for us. It produces a genuine probability distribution, so our weighted average is legitimate. Each position gets 1 unit of attention to spend across the sequence, and it decides how to split it. And it's smooth, so gradients flow back through it. Hold on to step 1, though, that stretching is about to cause the last problem. Here's the problem people skip. Dot products of high-dimensional vectors get large. Suppose the components of our query and key vectors are roughly independent, each with about unit variance. The dot product adds up d of those products, and when you add up d independent things, the variance grows with d. So the typical score size grows like the square root of d. With d in the thousands, root d is in the tens, and scores land in the tens or hundreds rather than near 1. Now feed those into the softmax we just built. Step 1 exponentiates, and the gap between a score of 80 and a score of 70 becomes a factor of e to the 10th. That's 22,000. The softmax saturates. One weight goes to essentially 1, every other to essentially 0. That's bad twice over. The model can only attend to one thing when the whole point was blending several. And the gradient through a saturated softmax is nearly 0, so the model can't learn its way out of the position it's stuck in. Training stalls. So instead, divide every score by the square root of d before the softmax. The scores had typical size root d. Dividing by root d puts them back near 1, which is the range where softmax is well behaved. That's the mysterious root d. It isn't a tuning constant somebody found by experiment. It's a variance correction, and the derivation above is the whole of it. Every piece now has a reason. Put them together. Read it right to left as a list of 5 repairs. V, take a weighted average, because uniform averaging destroyed the signal QK transpose. Score by content, because fixed weights can't adapt Q and K separately, because one vector can't both ask and advertise divide by root d, because otherwise the softmax saturates and gradients die softmax, because scores must become a distribution before they can be weights. Not a formula to memorize. 5 repairs in order, each one fixing the thing the previous step broke. And on our sentence, it produces a query. Every word produces a key. The dot products say board matches best. Dividing by root d keeps those scores in a sane range. Softmax turns them into 11 weights that sum to 1 with most of the mass on board. And it walks away carrying mostly board's value. The pronoun found its referent. No grammar rules, no parser, no dictionary, just 3 learned projections and a dot product. One consequence worth seeing, because it shapes everything downstream. Every position scores against every other position. N positions means n squared pairs. 11 words gave us 121 scores, which is nothing. But double the context and you quadruple the work. That's the wall behind every long context is expensive conversation, and behind an entire hardware industry, which is a topic of its own. It's also why the KV cache exists. During generation, recomputing keys and values for every previous token at every step would be catastrophic, so they're stored instead. And then that becomes the memory problem. What I simplified. This is single-head attention. Real models run many heads in parallel, separate query, key, and value projections, each learning a different relation, then concatenate the results. The mechanism is identical, there are just several of it. I also showed bidirectional attention, where every position sees every other. Generative models are causal. A position may only attend to positions at or before it, enforced by masking the upper triangle to negative infinity before the softmax. Same machinery, one mask. And I've said nothing about positional information. On its own, attention is completely permutation invariant, shuffle the words, and the output is the same set of vectors. Word order has to be injected separately, and how that's done is a genuinely interesting problem in itself. That's the next one. Next, how a model knows word order at all, when the mechanism we just built cannot tell a sentence from its own shuffle.